Hello folks, this is our part 6 video of the miscellaneous exercise chapter 1 and we are now to take up our question number 10. Let's see what the question reads. Show that A intersection B equal to A intersection C need not imply B equal to C. It's a kind of true or false kind of a statement. They give us a statement and they say it need not be true. If it need not be true, automatically we have to give a counter example. So the question says that, this is our question number 10. It says that given, they give us A intersection B is equal to A intersection C. That's given to us. You have to somehow show that B is not equal to C. That does happen. So for that we have to use a counter example, and let's see now how to go about going the counter example. For this we'll have to find out the set, and then we have to say that such a thing happens. So let's see how the set is. So this is our counter example. We, for example, let's have set A, maybe it is 1. I've told you that always take set as small as possible, so that's easy to manage. So set B you could have maybe 1 and 2. Set C maybe you could have 1 and 3. So what will happen? A intersection B. What is the intersection between A and B? Singleton 1. What is the intersection between A and C? That is also singleton 1. We have got the intersection with B and C, we have got them as singleton 1. That is how A intersection B becomes equal to A intersection C. We have them equal, their intersections are equal. But the set B is not equal to set C. That is what they have seen. But we observe that set B is not equal to set C. It's very clear to us that set B is totally different from set C. So that is what we are trying to show, that the given statement is not true. It does happen that whenever A intersection B equal to A intersection C, it's not necessary that B should be equal to C. We can have examples like this. That's how we show it by this counter example. Now quickly we go to the 11th question and see what they say. In the 11th question they say that A intersection X, they give us. It is given to us that A intersection X is equal to B intersection X, which is an empty set, and they also give us that A union X equal to B union X. They give us A union X equal to B union X. Both this is given to us. We have got to show that A equal to B. The question asks us to show that A equal to B. What do we have to show? We have to prove that A equal to B. Now this can be done in many ways. You can take it by set theory, A is a subset of B and B is a subset of A, like that show that A equal to B. Or you can take directly, use the properties, and with the help of the properties we can show it. We will be doing it with the help of properties and see how it works. So for the proof, let's consider A first. Proof, let's consider the set A. And because we have the theory already, we have shown that law in the previous question, we can take that law. It is coming very, very handy to us. A intersection A union X. By that law, we have learnt that union and intersection, we have the X familiar over here. So let's take it like this. Now A intersection A union X, because so much of data is there with us that A union X equal to B union X, A intersection X equal to B intersection X, we can take that data, we can use this data. Instead of A union X, we plan to write it as B union X. What is the advantage? It helps us to expand. We have our distributivity law. Let's expand and see what happens. This becomes A intersection, we have the distributivity. So A intersection B union A intersection X. Now what happens? A intersection X is familiar to us. We know that this A intersection X, it's being given to us that it is B intersection X. So let's take it as B intersection X, because that's given and we get it as B intersection X. We can call this, there's no harm if we call it as B intersection A. We know it is commutative. So for our convenience, we are calling it as B intersection A. It's the same thing. And the striking feature of this is that B intersection becomes common in both the cases. So we can bring our distributivity. So you have B intersection A union X by distributivity. You are using your distributivity, and with the help of that you are getting B intersection A union X. But A union X we know is equal to B union X. So we can revert back. and we get B intersection B union X. Well, what we are doing, we are using the property A union X equal to B union X. Like that, this is again going back to our property which we have learned in the miscellaneous exercise, and that way this comes to B. That's how our A becomes equal to B, and that is what is proved over here. So that's the proof of this particular thing, and we quickly move to the question number 12. In the question number 12, they say, find the set, it is an example, you have to give an example. Find the set A, B and C such that A intersection B, B intersection C and A intersection C are non-empty. A intersection B and B intersection C and C intersection A, they should be non-empty. At least one element should be there. You can have more elements also. But A intersection B intersection C is empty. All the three, when you do the intersection, it should be empty. But at the same time, when you take two set at a time and take the intersection, it should be non-empty. They are asking us to find such a set, that it is existing. That is why they are asking us to find it. So it's your duty to get those terms, those set like that. So the required example. Let's write the required example is, we are defining the set. Set A we should have, set B we should have, set C we should have. We have to only take care that they should have non-empty intersections, but together when you take it, there should be no intersection. So maybe here you could have element 1, 2, and then you could have here element 2, 3. Maybe here you could have element 3, 4. Even between A and C, there should be a non-empty intersection. So, I mean, yeah, between A and C, A and B should be having non-empty, B and C should be having, and C and A should be having. So, maybe we can introduce maybe 1. Let's check. So, what happens? What is the intersection between A and B? Between A and B, the intersection is 2. Between B and C, what is the intersection? Between B and C, the intersection is 3. How about the intersection between A and C? Between A and C, the intersection is this element 1. So that means all two sets, they have got some intersection. But let us take the overall intersection, A intersection, B intersection, C. Is there one common element which is there in all the three collections? No. There is no such element which is there in all the 1 and 2 is there here, 2 is there here, 2 is not there here. 1 is there here, 1 is not there here, but is there here. So like that. You take any element, it's not there in all the three set together, it's not happening. So that is why this is, there is no element here, it is an empty set. A intersection B intersection C, it is an empty set. That is the required example. Remaining questions, we are taking it up in the next video. Thank you.